Hello. So I'm Eloise Cardinal. We'll be starting this discussion now. So I am a transplant nephrologist at the CHUM and an independent researcher at the CRCHUM. And today I will be presenting with my colleague Tristan Sylvain, and I'll let him introduce himself.
So hi everyone, my name is Tristan Sylvain. I'm a PhD student at the Mila Lab from University of Montreal, supervised by Yoshua Banjo. And I've worked in the past on survival data, in particular using deep neural networks to address the different issues we currently have when modeling survival data.
So today, Tristan and I will be talking to you about the development of a clinical decision support tool to help transplant physicians and transplant candidates decide on whether to accept or decline an offer for a kidney transplantation. So this is a collaborative work, as you can see, and Tristan and Margot have been very much involved in the deep learning models that Tristan will be talking to you about later on. So chronic kidney disease is on the rise in Canada. And what I want to point out to you on this slide is that this is happening mostly in an elderly population with patients over 65 comprising the most new cases. And when the kidneys fail, well, some form of renal replacement therapy must be undertaken. And that can be in the form of hemodialysis. But of course, hemodialysis is quite cumbersome because it means coming to the hospital 3 times per week for 4 hours. We can also do dialysis through the peritoneal membrane, but this is also quite cumbersome. And the best treatment, of course, is kidney transplantation. And as we have an aging population with chronic kidney disease, we also have an aging population of kidney transplant candidates. And so why is kidney transplantation the best treatment for renal replacement therapy? Well, first of all, it improves quality of life, of course, but it also improves life expectancy. And when we look at the full cohort, we can see a gain in life expectancy of 10 years with transplantation in comparison to remaining on dialysis. So we would like to be able to perform kidney transplantations for every eligible chronic kidney disease patient. However, there is a problem in that there is a great gap, a great discrepancy between the demand for organs and the number of transplantations that we can perform on a yearly basis. And so how do we fill that gap and make sure that every eligible candidate gets a transplantation? So in an ideal world, this would be through living donation. But the problem is that most kidney transplant recipients do not have a living donor available. And 60% of kidney transplantations originate from deceased donors in Canada. And in the province of Quebec, that reaches a figure of 80%. So we must do most transplantation with deceased donors. And so another way to increase the number of transplantation and meet that gap is by increasing the deceased donor pool. How can we do this? So we can try to utilize for transplantation kidneys that originate from patients who have risk features for lower long-term graft survival. So here I'm talking about older donors with some comorbidities, for instance, hypertension, diabetes, or who have stroke as cause of death. And the idea of using these donors for transplantation is not new. We already perform these transplantations, but we know that we could optimize utilization of these donors because more than 20% of these donors are recovered but not transplanted in the end. So just to let you know a little bit about the context so that you can understand better the tool that we're developing. So in Canada, organ allocation is based on a provincial basis. So there are organ donation organizations ODOs, which manage all offers. So what happens, for instance, in the province of Quebec, our ODO is Transplant Québec. And what happens is that when a deceased donor becomes available, Transplant Québec will run an algorithm and give a score to each kidney transplant candidate who is waitlisted in the province of Quebec. And then the Transplant Quebec coordinators will start calling centers where the candidates are listed in descending order of the score until both kidneys are accepted or rejected. And so this score varies by province, but in Quebec, here are the elements that are given points for in the score. So for instance, wait time on dialysis. So the longer you've waited, the more points you get as a candidate. Elevated anti-HLA antibodies. This is because these patients are usually harder to match. So we give them points when we find a good match. Recipient age, the younger, the more points. Match. So closeness in age between recipient and donor age. And so that's important here that points are given for this closest in age in the tool that we're about to develop. And I'll come back to that later. And finally, they give points for compatibility in tissue typing between the donor and the recipient. And so the ODO does the allocation, but in the end, the final decision to accept or refuse the offer from the ODO belongs to the transplant physician in collaboration with the transplant candidate. And this should be in a process which is called shared decision making, where the transplant physician should be providing the patient with the relevant information for him or her to make the proper decision of accepting or refusing based on his values and what's important to the candidate. But the problem right now is that the quality of the relevant information is not very high. And so there is a need for a tool to guide physicians so that they can transmit the proper information to patients. And because the quality of the information is not very high, there is important variability in clinical practice in organs that are accepted or refused. And we know that there is variability by center and also by physician. And this has been described a bit everywhere around the world. And for those who practice in Quebec, it's very clear that there is variability by center. And so in order to fill that gap between organ demand and offer, the Canadian Blood Services is currently heading a national committee that has a mandate of optimizing organ utilization. So what does that mean? It means that we're going to be trying to use more of these high-risk donors. And of course, we're not talking about, giving them to children or very young adults, because we know they have a lower potential for long-term graft survival. But since we're facing also an aging kidney transplant candidate population, these are kidneys that could provide dialysis-free survival to our older candidates. But at the same time, if we're going to do this, we need to be communicating the risk of accepting or refusing an organ in a very detailed fashion, so that the recipient, the intended recipient, can take the best decision. And so to decide if we're going to accept or refuse a high-risk donor, one has to weigh the pros and cons of accepting or refusing. So if we accept this kind of offer, the pros are that there's no more dialysis now, which certainly will increase quality of life and life expectancy. But the cons are that you're accepting a high-risk donor. So this could lead to shorter graft survival, so earlier return to dialysis, and worse kidney function. But we know that both these things are risk factors for cardiovascular disease. So there are cons, but at the same time, we have to wonder how much shorter the graft survival with the current offer compared to what could be offered to me in general. Because as I was telling you earlier, there is age matching. There are points for age matching between the donor and the recipient. So if I'm a 70-year-old candidate and I'm waiting for that 20-year-old donor, I may be waiting a long time, and more wait time is not a healthy choice. So if we decide to refuse that offer, then the pros are that eventually we may get a better kidney, hopefully in a short term, on a short-term basis. But the cons, if we refuse, is that the candidate will have to keep on waiting, which reduces both life expectancy and quality of life. And then the candidate has to wonder, will I make it to transplant? Will I die on the wait list? Will I be permanently removed? And if this does not happen, how long will I wait to have a better offer? So in our effort to build this clinical decision support tool, first we did an end user needs assessment. So what we did is that we performed some focus groups with kidney transplant candidates and recipients in Montreal. And we also did semi-directed interviews with key opinion leaders across the country. And what we found out is that the appetite of patients for a web-based tool that they could be using was very low. That was our initial intention, but what we found from these focus groups is that our patients have placed great trust in their medical team, and what they expect is that their transplant physician will make the information, the relevant information, easily understandable and provide it to them so that they can be informed on their choice. They did not wish to use the tool themselves, and we have to remember why. The offer is a very emotional moment for them, and so they're certainly not thinking in the way they're usually thinking because of this emotional turmoil, let's say. And so in this clinical decision support tool, our idea is that 3 key points of information will be provided. The first one is, if we accept the current offer based on the donor and intended recipient characteristics, how long can we expect this graft to work? So how long do we expect that the patient will be alive and off dialysis? The second point of information is, if we decline the current offer, how long are we expected to wait for a next offer, and what's the relative quality of that next offer compared to the current one? Because we don't want to wait for nothing. We want to wait for a better offer. And the third point of information is a final suggestion by the tool to accept or decline the offer based on selecting the alternative, which will maximize survival with a functioning graft, so survival off dialysis from the time of the initial offer. So we have been working in the past 2 or 3 years on the first 2 points, the graft survival prediction and the prediction of wait time if the offer is refused. And first, we will be talking to you about the expected graft survival if the offer is accepted. And I will let Tristan present this part, which is very much machine learning, deep learning part.
Okay, thank you, Eloise. Can you move to the next slide, please? Okay, so as Eloise mentioned, one of the big components of the tool is actually being able to predict the survival probability of a graft. So what we did was, and this is work from a few years back, continuing up to today. What we did was we considered the SRTR cohort study, and we considered single kidney transplantations ranging from dates between January 1st, 2000 and December 31st, 2014. And we defined a censorship variable based on essentially if the event occurred after a certain date. And we did not exclude any previous organ transplants. And the outcome we were predicting for was the overall graft survival, which means that essentially we're looking at a variable which is graft does not survive if, for example, you have patient death, return to dialysis, or a need for a retransplantation. And we're considering in this work a set of variables comprising variables pertaining to the recipient, variables pertaining to the donor, and finally variables that are linked to both, such as the HLA mismatch. Next slide, please. So essentially, to discuss a bit this model, it's interesting to go back to the context of when it was first introduced. So essentially, what we did was, and this is work dating from 2016, 2017, so at the time, we didn't have too many approaches on deep neural networks applied to survival analysis. In fact, we were, I guess, the second work and the first one to actually introduce a more complex formulation of the Cox loss, the Cox log likelihood loss. Essentially, you have two different. So this can be seen as a general machine learning problem following the following assumptions. You have a target, and you have another variable, which is whether or not your event is censored. So the target would simply be, at this point in time, you have an event such as patient death or any of the other aforementioned events. And censoring simply means that after this specific point in time, you no longer have any information on the patient because potentially the patient has left the study or has disappeared for some reason. But it does not mean that the patient has died. It simply means you have no information. And what empirically we found was that it was, of course, very important to not only take into account the patients for which we have definitive information, but the patients for which we only have partial information in the form of all of the survival up to the censoring time. And what we did was essentially a multitask neural network where we predicted two things in this formulation. The first one was a ranking loss based on a predicted score, based on an intermediate layer of the network. And the second loss was simply survival prediction loss based on essentially the Cox log likelihood loss. And so, of course, as input to this model, we have the different features that I discussed before. Can you go to the next slide, please? Okay, and so what was really interesting with this work is that we actually got some very good improvements compared to other models. So I'll discuss quickly the baselines that we used. So Cox efferents is simply efferents approximation to the Cox log likelihood loss. The Cox log likelihood loss is, let's say, the gold standard for survival prediction. And efferents approximation is simply a modification to the loss to help it better take into account censoring that can occur, overlap between times. If you have multiple events at the same timestamp, then that complicates the computation of the loss, and efferents approximation to some extent solves this. MLP Cox was simply the first work on survival analysis applied to deep neural networks, and MLP Cox efferents would be simply efferents survival loss. And finally, random survival forests was at that time close to the state of the art for smaller data sets. And our model, as I mentioned before, is a hybrid of Cox efferents loss and a specific survival score that we added. Next slide, please. So I'll go over the advantages real quick. So first of all, we don't need extensive data processing. We also get good improvements in performance with this approach. We're able to take into account the full set of information available, so donor and recipient characteristics. And finally, we took an approach where we're able to predict the survival time directly, as opposed to simply a survival score, as would, for example, Cox's default log likelihood, as Cox's default log likelihood would predict. So this is actually very useful if you're a clinician and you want to give the patient some information on, their expected graft survival, as opposed to simply saying, well, you're high risk, you're low risk. So the disadvantages is mostly that we're using American data, which compared to the data in other countries has a significant domain shift. There's a lot of features which you might not have in different countries, which might, consider different inputs. And also, the survival rate is generally lower, which can be due to a reporting bias. So, for example, American hospitals are forced to report deaths or any negative events, whereas hospitals in other countries might not have to. So this could bias the output. But also it could simply lead to overall higher survival in countries such as, for example, Canada. And I should mention, as a final note, that we are working on improving this model continuously. Ideas that we worked on after this idea were mostly around improving the time prediction, which is, of course, very important for the aforementioned model. We got a workshop paper at ICML discussing the idea of applying this with an Earth mover's distance, where the Wasserstein distance between your survival distribution over time and ground truth survival distribution is computed. That gained a large improvement over time prediction. And we're also considering what happens in a more realistic case where, for example, your model is trained, but you have data coming in regularly in the form of simply hospitals every day adding more patients and more data. How do you improve your model in a way that does not disrupt past performance? And so I'm done. Thank you, Louise.
Okay, and so I'll be talking about the second point of information that our tool will provide now. And so this was work that was done by Jean-Noël Veller, a master student under the supervision of Andrea Lodi at École Polytechnique. And so the problem here is to say, so we have an offer at time t0, and we want to estimate the time to the next offer and the quality of that next offer. And so what Jean-Noël did is that he used data, real life data from Transplant Québec 2012 to 2017, and he built a model with Poisson distribution where what he did is that he looked to estimate future offers. He looked at the arrival of kidneys that had occurred in the 2 years previous to the current offer, and then, of course, he only kept those kidneys that could have gone to our recipient. So, for instance, he excluded those that had been ABO ineligible. He excluded those whose score was so low that they wouldn't have never been offered to our current recipient. And he also made a correction for the level of anti-HLA antibodies, or CPRA, we call them, because we know that these patients are harder to match. So he also corrected for that. And he updated all the predictions for wait time on dialysis, because you get more points as the time goes on the wait list. And this allowed him to predict the future of arrival of kidneys after a specific offer that was refused. And with these kidneys, he could also calculate the kidney donor risk index score, which is a score that's quite often used in the United States and gives an approximate quality of donor. And he could compare the potential future offers to the current offers in terms of quality. And now I just want to say a word about our industrial partner. And so how this came along was that the Federal Ministry of Innovation, Science and Industry and the CIHR funded a competition through Innovative Solutions Canada in 2019. And this was for Canadian companies to work with investigators of the CDTRP, the Canadian Donation and Transplantation Research Program, to develop a phase 1 study, proof of principle study that would enhance the use of AI in the field of organ transplantation and donation. And so COSIA, which is a company who does the IT work for Transplant Québec, won funds for this phase 1 study, and we started working with them, and we're halfway through the phase 1 study at present time. And what we're focusing on for the phase 1 study is a technology transfer of the developed models for the prediction of wait time if a current offer is refused and its quality. And we've been working on that and have 3 more months to complete this study. So all that we've been talking about for now, and Tristan mentioned a little bit about this, but we're talking about for now a static tool. But of course, in an ideal world, this would become a dynamic tool, a learning system where we could have access to other data sources, Canadian data, Eurotransplant data, UK data, Australian data. So there are registries a bit everywhere on kidney transplant outcomes. which could help us refine our predictions if we had access to real-time data eventually. Again, this in Canada, there is the problem of confidentiality because our registry does not give a lot of information on donor and recipient characteristics, but this data is found at the level of the centers. So this may be an eventual development. And here I would like to present to you the team. So, of course, as I was saying, this is a collaborative work. So, at l'École Polytechnique, Andrea, who supervised Jean-Noël, doing the time to next offer work. At Mila, here is Marco and Tristan, who were supervised by Yoshua Benjo to do the machine learning part with the help of also Joseph Paul Cohen, and at the CRCHM, well, myself and Marie-Chantal Fortin, and we did also the focus groups and the qualitative work on this project. So we will now be very happy, both Tristan and I, to take the questions. So I guess that I'm going to read the questions. So Uda is asking, do you account for the surgeon's performance in the transplantation procedure in your training data? If so, how does the learning curve seniority level impact the model? That's very interesting. No, the answer is no. I do not believe that this is available in SRTR, to my knowledge. And I do not believe that it would be easily accessible in any Canadian data either. And how do you compare your results to the current state and tools used by doctors in the hospital? Well, so we have never, we have not used our tool yet because it is not fully developed. But what I can say about the current clinical practice, which I do every day, is that at current time, the discussions around the offer are very, very much, very, very variable. Because what happens is that there's no specific script, there's no information that should absolutely be told to patients. So it's a bit like more an art than a science, and that's something that we're trying to fix. And so I have some colleagues who will say, for instance, we have a good kidney for you, and that's that. And other colleagues will go a bit in more details by providing, the KDRI and what it means in terms of percentage of survival at this or at 5 or 10 years. But we have nothing to tell you what happens if you refused at present time, which is why we think this is a significant addition to the current clinical practice. The second question is, can we access the presentation's recording? I do not know, but certainly the organizers can answer this. Oh, I see that there is another question. So, could you expand on why the access to the organ repository data is problematic? Would the use of federated learning to gather data dynamically without breaking silos be a solution? The answer is yes. That would be wonderful. So I think there are, so first of all, what we use is SRTR. So SRTR is available upon demand, upon presentation of a research project with approval from a proper ethics committee, and we have to pay to use it. It's not very expensive, but it is easily accessible, and we can update it and it's not very pricey to update it, after a few years. So that's easy. Now, the reason why we chose SRTR was also because there was a lot of observations, and Canadian data, of course, there's a population which is a lot less, but we do not have a registry that is as detailed as that which is in the States. So all the detailed data is at the level of the hospitals. So could we do a federated learning to gather the data dynamically? I think that would be wonderful. At CHUM, we have a data lake, which is managed by Michael Chassé and his team. And so, this is the kind of structure that could be helpful for our project. But I know there's something like that at McGill as well, but I don't know how much of this type of structure there is in other centers. Thank you all very much for attending. Thank you very much, Tristan, for co-presenting with me.
Thank you.